Well, good morning, good afternoon, and good evening, and welcome to part 2 of our webinar series, Risk Mitigation in the Pharmaceutical Laboratory. My name is Isabelle Vutrieux, and I will be hosting this session. It is my pleasure to welcome Lise Gauthier from Waters Corporation, who will discuss improving method transfer with intuitive innovation. But before I hand it over to Lise, I would like to share with you a few pointers to help you navigate the webinar platform. We invite you to use the Q&A box to ask your question. You should see it in the middle of your screen. And we will set aside some time at the end of Lise's presentation to address your questions. One question we actually often get is about accessing the presentation post-webinar. So I want to share with you that as a webinar registrant, you will receive an email within 48 hours after the event with a link to the webinar recording. And in addition, a list of resources with application notes related to today's presentation is available in the bottom left corner of your screen. On the right-hand side of your screen, you will find a survey. Your feedback is very important to us, and we would really appreciate if you could take the time to complete the survey before you log out today. So today we will discuss a topic that many of you have asked us about: how to improve method transfer outcomes. Our presenter is Lise Gauthier, Principal Scientist within the QA QC Business Strategy Group at Waters Corporation in Milford, Massachusetts. Lise has been with us since 2014, and prior to joining Waters, she worked as a scientist for AstraZeneca for about 20 years, holding positions of increasing responsibility within QA and discovery. So welcome, Lise, and over to you.
Great, thanks, Isabel. Today, I'm going to provide an overview of how method transfer outcomes may be improved with the Alliance IS HPLC system. Waters has recently introduced the Alliance IS HPLC system, which was created through years of collaboration and research between Waters and QC labs. The system, which runs on the Empower chromatographic data system, is intuitive to operate, and it was designed to reduce common errors, improve productivity and efficiency, and improve the reliability of analytical measurements. This combination of features makes method transfer faster and easier. The Alliance IS HPLC system is a quaternary system with a flow-through needle sample manager and a TUV detector. This is a configuration that's probably familiar to most of you since it's the most common configuration used in QA/QC. Each module of the system contains a number of design innovations, which I'll go through in this presentation, and I'll provide some examples of how these innovative designs can help with your method transfer. The Alliance IS system has many features not commonly found in HPLC systems, while providing the same or improved results as compared to legacy HPLC systems. These performance or design features include an outer puncture needle for improved robustness, optimized needle wash design to reduce carryover, and a new check valve design designed to improve performance under challenging high organic mobile phase conditions. In addition, there are tool-free fittings for common touch points to reduce the risk of any voids negatively impacting chromatography. Other key performance improvements include carryover, injection precision, and detector sensitivity, which enable the Alliance IS HPLC system to meet or exceed the performance of the legacy Alliance E2695 system and competitive HPLC systems. There are a number of considerations for adopting modern LC technology in a global economy. The decision to transfer products between sites is frequently driven by economics, and it can involve a fair amount of complexity due to the interrelationship between various departments, laboratories, and sites. With respect to liquid chromatography, Analytical method transfer can mean many things to many people. For some of you, it's taking a method that uses a large particle column and scaling it to a smaller particle column to improve productivity. For others, it could be a simple technology transfer from one lab to another. Analytical method transfer could also mean leaving the method as it is by transitioning it from one instrument platform to another. Each of these scenarios comes with its own set of challenges. Oops. The Alliance IS HPLC system has many key attributes that support successfully moving a method from another HPLC system. These include the Method Translator app, which enables a method from an Alliance or an ARC, as well as other competitive systems controlled through Empower, to be converted to an Alliance IS HPLC method. In addition, the dwell volume of the system can be entered into the touchscreen, providing a record for the system. To aid with method transfer, the dwell volume of the system can also be adjusted with different mixers. These features, along with the expanded performance range, facilitate moving a method from another HPLC system to the Alliance IS HPLC system. The Alliance IS HPLC system is targeted for use in QA/QC, and because of that, we know that one of the most important considerations for end users is the successful transfer of their existing methods to the Alliance IS HPLC system. Internally at Waters, we've done extensive work to ensure that our customers will be successful. Over the next few minutes, a number of method transfer examples will be discussed, but the full range of our testing is showcased in this slide. To simulate existing validated methods, we used a variety of USP methods, along with 2 methods that we developed in-house. These methods cover several chromatographic modes, and the methods were transferred from a wide range of HPLC systems, which included not only Waters LCs, but comparable systems from competitive vendors. Oops. First, we'll review the Method Translator app, which enables users to transcribe instrument methods within Empower. This reduces the risk for any manual transcription errors. So let's discuss some of the key features of the Method Translator app, which is also referred to as the IMTA, or the Intelligent Method Translator app. The standalone application is accessed through the Empower via the Apps menu in any project. The app provides the ability to translate an Empower instrument method for select systems into the Alliance IS HPLC instrument method editor. The steps of this process include first selecting the method to be translated, which is followed by automated translation of the method. Next, the user reviews the translated parameters and then saves the methods as an Alliance IS HPLC method. Finally, there's a translation report generated. There are a number of benefits to using the Method Translator app, including elimination of transcription errors, time savings, and complete traceability with Empower with the compliance. This slide shows the translation process using an instrument method that was originally created on an ARC system. Once the app's been opened, the original instrument method is chosen from a drop-down menu which shows all of the instrument methods contained within the project. The method is automatically translated into an Alliance IS HPLC method. The method is presented for review, and then the translated Alliance IS method is saved. The saved method includes a note clearly indicating that the method was generated using the Translator app for traceability purposes. Finally, the report is viewed, showing the key method parameters from both the original method and the translated values contained within the Alliance IS method editor. The app delivers a translated method into the Alliance IS HPLC method editor. In this example, the Alliance IS gradient table is shown on the right. However, all key instrument parameters can be translated. These can include the flow rate, the column temperature, wavelength, and sampling rate. The app allows a user to select an ARC, Alliance, or select modules from other manufacturers for translation. Here's an example that'll showcase the benefits of using the Method Translator app. This slide shows the results for the USP ibuprofen tablets organic impurities method that we ran on 4 different HPLC systems in our labs. System suitability results were met on all of the systems, but looking at the signal-to-noise ratio, the results for HPLC System 4 are significantly different from that of the other systems. So we asked why this was. Should we ignore the results since the system suitability criteria for signal-to-noise was met, or should we just blame the instrument? While these might be the easiest things to do, it's important to review the data to find the root cause of the lowered signal-to-noise ratio. By digging into the data a little bit, specifically reviewing the instrument methods that were used to acquire the data, the problem became apparent. The original method that was used for the ibuprofen impurities method specified a TUV data rate of 2 Hz. When the method was translated to the Alliance IS HPLC system, the Method Translator app was used, so the correct method was translated and run, and resulted in an expected signal-to-noise value of 86. When the method was transferred to HPLC System 4, which was not an Alliance IS HPLC system, the Method Translator app wasn't available for use. The method was manually entered, and the user accidentally forgot to enter a sampling rate into the method, so the default data rate of 10 Hz was used. This high data rate for this method resulted in oversampling, which led to a significantly higher noise value, which resulted in an overall lower signal-to-noise value. Let's look at some of the system-level parameters that have an impact on method transfer. Dwell volume is the volume between the point of mixing and the column inlet. It's impacted by tubing length and an internal diameter, and mixers and valves in the fluidic path before the head of the column. Differences in dwell volume result in variation of retention times between systems. The impact of different dwell volumes on retention time was evaluated using a method for the separation of a generic test mix. The method has an isocratic hold at 20% B at its start, followed by gradient conditions to 90% B. The separation was run on an Alliance IS HPLC system, a legacy Alliance E2695 system, and a comparable system from a competitor noted here as System Y. In the chromatograms, the first 2 peaks elute during the isocratic hold, so we don't see the impact of dwell volume differences. But due to the variation in dwell volume between systems, the differences in retention times are seen for the remaining peaks. Relative retention times, however, are the same across the 2 systems. Variation in retention times that result from dwell volume differences between systems can be mitigated by adjusting the gradient start relative to the injection. Such adjustments for dwell volume differences are allowed per USP General Chapter 621. Adjustments to the gradient start are easily made through the Alliance IS method editor. In this example, the generic test mix was run on the Alliance IS HPLC system using a method without dwell volume compensation, and with a method that was compensated for the difference in dwell volume between the Alliance IS system and a legacy Alliance system. The resulting chromatograms shown here show that the compensated method produced retention time shifts that align with the retention times obtained from the legacy Alliance system. Another system-level parameter that impacts method transfer is extra column dispersion. Extra column dispersion is the extra column volume in an HPLC system, and it includes the volumes from the injection port to the valve to the passive preheater, and the column outlet to the flow cell inlet. Extra column dispersion affects peak width, resolution, and the overall efficiency of separation. The effect of extra column dispersion on a quantitative assay is shown here. The most critical part of transferring methods between systems is ensuring that key performance requirements are met, including quantitative results, regardless of the system that's being used. Here, a sample of quetiapine fumarate drug substance was analyzed per the USP math assay on both a legacy Alliance E25 system and an Alliance IS HPLC system. The same sample and mobile phases were used on both systems. The assay results were nearly identical between the two systems, as is the chromatography, but the Alliance IS, which has a lower extra column dispersion than the Alliance E2695, shows a slight improvement in peak tailing and improved resolution of the small impurity peak that elutes on the main API tail. Although it provides the same quantitative results, the improvement in chromatography allows for easier and more reproducible integration. Now let's take a look at the bottle tray. Although it might seem trivial to you, a lot of thought and design effort was put into the bottle tray. In addition to holding the solvent bottles, the tray also includes a status indicator light which quickly identifies the state of the system as idle, running, or in an error state which requires attention. The front of the tray is see-through to make determining the solvent levels in the bottles easier for the user. You'll also notice that the solvent bottles have been designed with caps and labels, which makes identification of the solvent lines easier. Here's an example of a situation that probably all of you have experienced at some point. Perhaps it was the end of the day and you were rushing, or you were distracted and you mistakenly put the aqueous line into the organic bottle and vice versa, and you didn't realize the mistake until your chromatography looked strange. Most current systems have small labels on their lines, which can make mixing up the lines quite easy. In contrast, the Alliance IS has large solvent flags which sit in the bottle caps. This allows the user to quickly identify which lines are in that bottle. Now let's move on to the pump and talk about some of the features that aid in method transfer. There have been a number of changes to the pump design, including newly designed check valves and a self-priming seal wash pump. These improvements in design provide exceptional performance and robustness of solvent delivery. This example highlights the improved performance of the pump through the transfer of the USP azithromycin organic impurities method across multiple HPLC systems. The method is challenging for a number of reasons. It includes a gradient of an aqueous sodium phosphate buffer with 100% organic. The gradient starting conditions are 50-50 A to B, and the gradient runs to 75% B. This mixing of buffer with high amount of organic has the potential for salt to precipitate within the system. The method also includes an initial gradient step of a 5% change in composition over 25 minutes. That's a 0.2% change per minute, which is challenging for a pump to deliver reproducibly, especially a low-pressure mixing pump. And finally, the method requires UV detection at 210 nanometers. Such a low wavelength has the potential for baseline challenges. The azithromycin method was initially run on a non-Waters HPLC system. The results show significant retention time wobble over the course of 6 replicate ejections, as seen in the chromatograms on the left. Looking at the pressure traces on the right, you'll see that there's a lot of instability in pressure. In fact, injection 1 shows a complete dip in pressure to almost zero at approximately 80 minutes. This is likely due to precipitation of salt somewhere within the flow path. The same trend of pressure dips was seen across multiple competitive systems, but it wasn't seen on the Alliance IS HPLC system. The overlaid chromatograms for 6 replicate injections are shown for all 3 systems. For HPLC System 1, there's not only significant retention time reproducibility problems, there are also spikes in the UV baseline occurring at random intervals. This isn't ideal for a number of reasons, but mainly because it can lead to errors in identification and quantitation of impurities, or worse, the whole analysis might have to be repeated. HPLC System 2 also suffers from non-reproducible retention times, but this system showed random dips in the UV baseline as opposed to spikes which System 1 showed. Again, this data is less than ideal. The data collected on the Alliance IS HPLC system shows very reproducible retention times, stable pressure indicating that there's no precipitation of salt, and a smooth and reproducible baseline. This leads to confidence in both peak identification and in quantitation. Transfer of the tryptophan organic impurities method also has potential challenges, this time associated with the use of trifluoroacetic acid as a mobile phase additive and a UV detection wavelength of 220 nanometers. TFA is a commonly used ion pairing reagent used in HPLC, and it strongly absorbs at wavelengths below 250 nanometers, so any small variations in concentration results in baseline ripples. Low-pressure mixing pumps, which deliver solvent by packeting, enhance this baseline rippling effect. Ripples in the baseline can cause challenges in signal-to-noise, consistent integration, and in quantitation. And this is why most instrument vendors offer a high-volume TFA mixer, which is designed to deliver smoother baseline, but it's at the expense of a larger dwell volume. In this example, 2 mixers of similar volume but different mechanical design were run on the Alliance IS HPLC system to evaluate the impact on baseline and signal-to-noise for the USP organic impurities method. The standard mixer has a volume of 675 microliters and comes as a default mixer on the system, while the diffusion bonded mixer has a volume of 690 microliters and it's optional. Here are the resulting chromatograms for both the blank and the standard acquired with each mixer. Visually, it's clear to see that the diffusion bonded mixer results in a much smoother baseline. This is also confirmed numerically with a calculated signal to noise for the standard solution almost 10 times greater for the diffusion bonded mixer. This is because the noise value was significantly reduced, not because the peak signal was larger. This highlights the improvement in performance when the diffusion bonded mixer is used with TFA containing mobile phases. Methods using different modes of chromatography can be run on the Alliance IS HPLC system. There are a few considerations for switching between modes. When switching from reverse phase to Hillock, no hardware changes to the system are needed. Some considerations for switching between reverse phase and Hillock are to ensure that the needle wash is appropriate for the analysis. You want to match your injection solvent as closely as possible to the initial method conditions, and also flush salts from the system before you introduce high organic Hillock mobile phases. You also should monitor the UV and pressure channels to confirm equilibration. When switching from reverse phase to normal phase, there are some hardware changes that are needed. The pump check valves and the waistline tubing need to be replaced, but these changes are easily and quickly made. And unlike some other systems, the pump seals do not need to be replaced. To run normal phase methods, the system needs to be transitioned to normal phase solvents. All water must be removed from the system before normal phase solvents are introduced. This slide shows how the Alliance IS HPLC system can run different modes of chromatography. A gradient Hillock method for the separation of 7 water-soluble vitamins was run. The method met system suitability criteria and was used to quantitate folic acid and vitamin B12 in a vitamin supplement. An isocratic normal phase method for tocopherols was also run. The check valves and waste tubing on the system were replaced, and the system transitioned to normal phase solvents by flushing the fluid path with IPA. A standard containing 4 tocopherol isomers and a sample of vitamin E were prepared and analyzed. System suitability criteria were easily met and the tocopherol isomer content in the sample calculated. Moving on to the sample manager, it includes a flow-through needle design with puncture needle. It can hold 3 well plates or vial trays, including a 54 vial tray option. It has self-identifying sample plates with a barcode reader and vial well bottom sensing. Here's an example of how the improved sample manager design can help in method transfer. This example involves a USP method for the organic impurities in cetirizine hydrochloride, which is an isocratic Hillock method. The method's been run in our lab on several different HPLC systems. On HPLC System 4, a strange peak shape and peak splitting was seen. Troubleshooting on the system included re-preparing the solvents and samples, re-equilibrating the column and system for up to 24 hours, and trying a different column, none of which resolved the issue. Next, the samples and mobile phases from System 4 were run on one of the other systems, and that chromatography looked good. Since none of these approaches explain the results, we next looked at the system mechanics and how HPLC System 4 differed from the other systems. And we found that the needle wash mechanism for HPLC System 4 was significantly different from the other systems. For the analysis, a very aqueous wash solvent was used, and under Hillock conditions, this is a very strong wash. HPLC System 4 uses an older style needle wash where the needle is dipped into a vial containing the wash liquid. Residual wash solvent, which contained high percent water, was left on the needle, and it was being injected along with the next sample, causing the peak splitting. The chromatograms show how changing the amount of water in the wash affects the chromatography for both HPLC System 4 and the Alliance IS HPLC system. On HPLC System 4, as the percent water of the wash solution increases, the peak shape distorts. On the Alliance IS HPLC system, the peak shape is unaffected by the increasing water content due to the optimized needle wash design. Another way in which the sample manager design can help improve method transfer by reducing errors is shown through some data obtained from running the USP quetiapine fumarate assay. This assay was run on an ARC HPLC system, which has a low-pressure syringe, and on the Alliance IS HPLC system. System suitability parameters were met across the two systems, and the assay results obtained for a sample were comparable. So what was the problem here? If you compare the chromatograms, you can see it. The quetiapine peak in the system suitability solution should be saturating the detector. We've run this analysis in our lab many times on many different systems, and we have control charts that monitor our data. The control chart shows an atypical decrease in sensitivity on the ARC HPLC, so we investigated why this was. First, we looked at the results obtained for the system suitability solution, the standard, and the sample preparation across the two systems, and a signal-to-noise decrease was consistently seen on the ARC HPLC system. Samples were remade and split across the two systems, and once again the ARC HPLC signal was approximately 1/5 of that seen on the Alliance IS HPLC system. Upon investigation, the issue was determined to be a volume configuration error on the ARC HPLC system. The low-pressure ARC HPLC syringe requires manual volume configuration in the software. It was discovered that for this analysis, the system was configured with a 500 microliter syringe, when in fact the actual syringe involved was the default 100 microliter syringe. For the low-pressure syringe used on the ARC HPLC, the volume delivered is equivalent to the total syringe volume divided into 100 motor steps. So when a 500 microliter syringe is configured, 5 microliter per step is delivered, and when a 100 microliter syringe is configured, 1 microliter per step is delivered. In our example, a 500 microliter syringe was configured and the injection volume was 50 microliter, which equates to 10 steps. But because the actual installed syringe was 100 microliters, these 10 steps only delivered 10 microliters, which is 1/5 of the volume required for the analysis, and it produced 1/5 of the expected UV signal. This error in volume configuration cannot occur on the Alliance IS because the Alliance IS system doesn't require manual volume configuration. This type of error is prevented from occurring. Another example of how the sample manager design improves performance is shown here. The method is the USP assay for ketoconazole. The dissolution of standards and samples in 100% organic and the low area percent RSD requirement for system suitability present potential challenges for a successful analysis. Here, you can see the results obtained on an Alliance IS HPLC system versus competitive systems. Replicate injections of the standard are shown on the left, and you can see that there's good reproducibility on the Alliance IS HPLC system, with an area percent RSD of 0.09%, while the competitive HPLC system 1 doesn't have as good reproducibility, with the area percent RSD being 1.24, which is above the system suitability limit specified in the monograph. The charts on the right show the reproducible performance of the Alliance IS over time as compared with that obtained with two competitive systems. Overall, the Alliance IS was consistently capable of meeting system suitability criteria, demonstrating how the sample metering pump design improves the performance with 100% organic diluents. The column compartment has been completely redesigned and now comes as a single heater cooler, which covers a temperature range from 4 to 90 degrees C. It can accommodate a column of up to 300 millimeters in length and an internal diameter of 8 millimeters. Both column connections have a tool-free fitting designed for both ease of use and a zero dead volume connection. Finally, the Alliance IS system and Empower 3.8 introduce eConnect column technology, which is facilitated by the near-field communication reading capability of the column compartment. In this example, you can see how an eConnect column prevents errors. We ran the USP quetiapine assay method, and the results had a retention time that was significantly different from what we expected based on previous analyses, as you can see from the outlier in the retention time control chart. The column required for the assay is a C8, but we found that a C18 column of the same dimensions was accidentally installed on the system. The Alliance S.A.S. system with Empower 3.8 and eConnect columns prevents this type of error from occurring. eConnect columns have a near-field communication enabled tag on them. After the column is installed in the column compartment, the system automatically detects and reads the data from the tag and sends it to Empower. When an analysis method is created in Empower, a column is specified, and before the system starts the analysis, it checks the column specified in the method against the column installed in the column compartment. If they don't match, then the analysis does not start, and the user is notified that the incorrect column was installed. Moving on to the detector, there are a number of new features, including self-identifying flow cells and lamps and improved sensitivity. The ibuprofen tablets USP organic impurities method provides an example of the improved sensitivity. This is an isocratic method that has a system suitability requirement for sensitivity with a signal to noise of not less than 10 required. This is a typical of many regulated methods, especially in purity methods. Given the recent changes to regulatory guidelines, the performance of all the systems was evaluated with signal to noise calculated in 3 different ways as shown here, including using a blank at 5 and 20 times the peak width at half height, as well as a flat part of the baseline in the isocratic method. The Alliance S.A.S. system produced the best overall performance when compared to legacy HPLC systems with the highest signal-to-noise values. Here's another example of the improved sensitivity of the Alliance S.A.S. HPLC system, this time using the Hillick cetirizine hydrochloride organic impurities method. The system suitability requirement for signal-to-noise is not less than 10. Following the USP General Chapter 621, signal-to-noise was calculated from a blank injection using 5 times the peak width at half height. The Alliance S.A.S. HPLC system produced the best overall performance compared to legacy HPLC systems, with the highest signal-to-noise values showing the ability to regularly meet the stringent criteria. So in summary, today I've shown that the Alliance S.A.S. HPLC system, which was designed with the user in mind, has improved performance over many legacy systems. The system provides many features designed to facilitate method transfer, which includes a method translator app, which allows for transitioning Empower instrument methods to Alliance S.A.S. methods. The system is easy to operate and has features designed to reduce errors while providing confidence that the same quantitative results can be realized as obtained from legacy HPLC systems. And with that, I'd like to acknowledge my Waters colleagues who produced all of the data that was included within this presentation. Thank you for your attention.
And thank you, Liz, for your presentation. That was excellent. So we will now move to the Q&A session. And Liz, I invite you to turn on your camera, please. And while you're doing this, Liz, I would like to remind our audience that questions can be entered in the Q&A box on your screen. So we have a few questions already. And let me ask the first one. So Liz, are you able to, oh, okay. Let me ask the first question. Okay. So you showed us the touch screen. What is it used for, Liz?
So the touchscreen is used for tasks that the user typically performs at the instrument. This includes things like configuring your solvents, the volumes, and the expiration dates. It includes priming. It has workflows for things like system startup and system shutdown. It also has some guided maintenance workflows. The pre-run checks and the runtime checks are also enabled to the touchscreen. The touchscreen can be fully operated while wearing gloves. You cannot make an injection through the front panel. The injections are made through Empower for compliance.
Okay, very good. We have a couple of questions about software. The first one, you should be able to see it on your screen now, is about whether the system can be run through a chromatography data system other than Empower.
No, the system was created to be run through Empower. It runs on Empower 3, feature release 4, and higher.
Thank you. We have another question related to Empower. Do you need to be logged into Empower to access the touchscreen?
No, you don't need to be logged into Empower to access the touchscreen. While you are running in Empower, the touchscreen is locked, so you can't make any changes while it's running. However, it is possible if you need to make an emergency stop, you can do that through the touchscreen while running in Empower.
Okay, good to know. The next question is related to the eConnect columns. So I guess it's a question that we actually often encounter. Do you have to use an eConnect column on the system, or can it be another column?
No, you don't need an eConnect column. You can use a Waters column that doesn't have that capability, or a competitive column. However, since you don't have the near field communication enabled tag on the column, you're not going to get the column information sent through Empower. So your check where you check to make sure the correct column is installed won't be enabled, but you can run other non-eConnect columns with the system.
That's going to be very helpful for our audience. Another question about columns and about the column oven. Can you fit more than one column? And if so, how many can you fit in the column oven?
So you can only fit one column in the column oven. It was designed for one column up to 300 millimeters in length and 8 millimeters in diameter.
Okay, great. And we now have a question that I've actually ever heard many times about the texture. So you mentioned that the system is currently available with a TUV detector. Are there any plans to have a PDA detector with the Alliance S.A.S HPLC system?
So we are currently exploring that option. However, at the moment, the only detector that is available with the system is the TUV.
Okay. And I don't see any other questions in the chat. I guess at this point, I will thank you, Liz, for your insights, and thank you all, the participants, for your questions. I invite everybody in the audience to complete the survey. It should be on the right-hand side of your screen. We really value your feedback, and we want to know what topics could be of interest for future webinars. The next one, so part 3 of our webinar series, will be held on August 30th, so in 2 weeks, same time. And our presenter will be Neil Lender, who is a principal product manager in the informatics group at Waters Corporation. Neil will show us how to create efficiency in your routine LC workflow with simple automation steps in Empower. So you don't want to miss it. August 30th, same time. And this brings us to the end of this webinar session. You can still answer the survey. We'd love to have your input. I want to remind everyone that an email will be sent to all registrants within 48 hours with a link to the recording, so you can watch it again or you can share it with your peers. And with that, I would like to thank Liz and all of you, and hopefully we will see you on August 30th. Thank you very much and enjoy the rest of your day.